Okay, welcome everybody. Hope you enjoyed your lunch. I quickly gonna present the use case. My name is Remo. I'm the network automation engineer at zebbra, and my colleague Leandro Lerena will get in some nitty-gritty details about some particularities of that use case. We were asked by one of the biggest retailer in Switzerland to support them by a switch of the ISP provider. The time was really short. It has to be done by the end of next year, and they approached us in autumn. So we had in total like 14 months time to come up with a concept, do some proof of concept, some piloting phase, and then start in the execution phase. There were over 1,000 locations, different stores, completely different setups, like the really big discounter stores or retail stores, some fitness centers and whatnot. Very diverse, from very small to very big, and there were no standardized layout around. We achieved 85% of the locations by the end of the time, which was quite a nice result. Just to remind you, a modern retail store is like filled with smart devices. Everything is relying on a stable network. You have some Wi-Fi scanners, which you may know, or billboards and price tags. Everything is relying on a stable network. So there were some requirements, like the store stays always online and functionally. The migration had to be done during the night without any staff on site, no user interaction at all, through end-to-end automation, and fully auditable. We came up with a process, nothing unusual. First, you had to build the equipment, new ISP has to build it. We had some preparation task where we checked the readiness, the migration itself, and afterwards the validation phase to check if everything was back as good as it was before, or even better maybe. If the validation wasn't successful, we had the automated rollback, which could be performed even autonomously in case we completely lost connection to the site. But if everything went right, we proceeded to the decommissioning phase, where we get rid of the old ISP configuration and even sent the resignation letter to the ISP to cancel the line. And now Leandro will take over and cover some details.
Yeah. I think there's one slide in still, but it's just about the real process, which is a bit more complicated, but we're not going to go in that much detail.
Tend to ignore that one.
Yeah, it's painful. But we want to stay a bit on the high level. So in the first part, we will talk a bit about challenges in doing automation like that, end-to-end automation of a process, especially challenges of scripts. And then in the second part, we will present our approach to it, which is going to be like a workflow as a transaction. So for the first part, please keep in mind some of the marked points here. In particular, robustness, no service downtime, and automatic rollback capabilities. So it's a lot about transactional behavior, of course. And it's also clear that it's not only configuring devices, but also talking with a lot of APIs and a lot of other systems. Okay, and then following up a bit on the talk of Damien, which was really nice, I want to present a first challenge, and that is the challenge of racing conditions. And we can have racing conditions. It's pretty easy to get them, as you may know. Especially if we are running operations in parallel. So I brought a small example for you. And here we have two actors that will interact with the same device. And they have really simple tasks. The first task is set port 1 to state up. And we will quickly going to see what happens when we do this in a non-atomic way. So we will first read the whole configuration. We will update it locally, and then we write back the configuration in the device. So this script will obviously terminate successfully. It will have an exit code 0, let's say. And now we see when we do the timing, a bit unfortunate, then we have a similar script with the same structure actually, and it will set the port 2 to up. And now you can already guess, we do the same thing. We see, we read config, we update config, and we write config back. From the point of view of the second operation, from the second script, this will also be a successful operation, but the end result looks not like what we desired. So we have here a change of the first operation that is overwritten. And also a bit following up on the talk of Damien, both of these scripts are idempotent, so they're a pretty nice property already, but it's not enough to tackle this situation. So how could we solve that? Of course, we could move the burden to the scripts and just say you need to take care of it in the script itself. But if we had a central coordinator, then we could use a so-called pessimistic locking approach. Of course, we need to know which scripts will be executed. But if we knew that, then we could apply such strategy and just give the lock to one script first. It can execute, it can terminate successfully, and then we just move the lock over to the second script. So this is one central approach in our solution. So keep that a bit in mind. It's also a simple. Sorry, I need to go to the end. It's also a simple example, of course. But I challenge you. Maybe you can think in your automatization world what could go wrong. So it has nothing to do with declarative and non-declarative way of defining a task. It's really what is in the end executed and in which time. Okay, then the second challenge is, of course, failing scripts, and also here we have some tools or some nice properties that we can build upon, and this is knowing what is a failing operation. So a failing operation can sometimes be reverted. We call this rollback. This is pretty important when we want to achieve transaction-like behaviors. Some operations can be retried. We heard this morning very nicely. So this is called idempotence property. We can just reapply a config over and over again, and there's we do not expect that anything will be different if we apply it multiple times. And then we have some very nice functions that are guaranteed to not even have any negative effect on the network. And we call this in our presentation just the pure functions. So it could be like reading a config or fetching something like that we can retry. But if it fails, we can also just discard it, and we know we did nothing bad to the system. However, scripts are often unstructured, and it's very hard to be sure what properties a script really has. So what happens if we apply it twice? Can we roll back it? So this is not that easy. But our leading question is basically what can we achieve when we would declare these properties, if we would know how a function does behave. And that brings us to our solution approach, which is called the workflow as a transaction, where the first thing that we did is asking ourselves what is really the best we could possibly ask for. And this was also mentioned this morning, so it was a great start in the day when we heard this, because it's basically that. It's basically a classical database transaction where we could just start a transaction, create a try block, and just execute all the steps that are needed to come from point A to point B. And if anything wrong happens, anything unexpected happens, we can just roll back and try again tomorrow. No need to wake any engineers up in the night. So that would be the ideal world. And if we had that, of course, we had these nice little ACID properties that I'm sure every one of you knows them. Maybe it's a bit in the not so accessible memory, but it's not really important. They just guarantee us that in the end of a transaction, we are either in the initial state, so nothing has changed, or we are in the desired new state and everything is working fine. And of course, this is not realistic. Why is it not realistic? I have just a little example why it's not realistic. In general, the reason is non-reversible actions, of course, but we can, for example, brick a system with a firmware update or something of this kind. So we cannot really assume that to base a system on ACID properties. But what we can do is we can ensure isolation. This is one of the key elements of our approach. So we can actually declare in some way on which devices a script or an operation will run on, and we can design workflows in a way that they fail really early. So we do more checks in the beginning, and we check if it's safe to run the more dangerous operations afterwards. And that leads us to our goal, to achieve transaction-like behavior for multi-step workflows, which is, again, not really realistic. But stay with me a second. Our building blocks are pessimistic locking, so to ensure the isolation property of the ACIDs properties, this is kind of easy. And then we know the properties of the function blocks, of the steps, let's say, of a workflow. This is our assumption that we can declare them in some way. And then all the model violations, we capture them in a separate state that we call failed unsafe. So you see here a life cycle of the workflow. It can complete successfully. This is fine with a transactional model. We can fail in a safe way, so the transaction will not have any effect on the network. This is also fine with a transactional model. And the only thing is, if we are failing in the middle of a workflow, we don't know what to do. We are kind of stuck in the middle, and this situation we just annotated with a failed unsafe, which will then potentially trigger an alarm to a network engineer. So let's look how this would look like when we migrate point of sale in the example that Remo presented. The first step would be we lock all the devices, so we make sure that when our workflow is starting to run, then no other manipulation or check or automated tasks can access this device. And then we have the first step, like in this example, fetch config. And fetch config, we call this a pure function because it will just read a configuration. It will not overwrite anything. It will either fail or it will succeed. If it fails, we know we did not touch the network yet, so we can fail safe, actually. We can try again tomorrow, no need to wake anybody up. The same is true for pre-check. So in the pre-check, we do, for example, check for the opening hours. Here again, it's a pure operation. We can just abort the whole migration if something is wrong. We did not yet touch anything. So that's easy. And then the next step would be to actually perform migration, actually change something on the device. And here we can see two scenarios. The first scenario is the function is idempotent. If that's true, we can just retry a bunch of time, see if it's maybe just a temporal issue. We can reapply like 5 times. If it still fails, then we can check, is this a revertible action? Is there a rollback function? If yes, we can also roll it back and fail in a safe way. No need to alarm anybody. But if this is also not the case, then of course we go in a fail unsafe state where we violate our transactional model. So this is basically the escape route of the transactional model. And then, of course, after the migration, we do a post-check. Post-check is, again, a pure function in this sense. We can retry it. We do not change anything in the network. We just analyze the network. But of course, it comes after a non-pure step. So also here, if the post check fails, we are at risk of transitioning in a failed unsafe state. So this is just a bit to present the idea how we approach transactions. In the end, of course, we unlock again our context so that other workflows may run on it. We do that only if we are not in a failed unsafe state, because a failed unsafe state does not allow us to know if it's even safe to run something else. So this would lead to a manual intervention. And then we update the internal knowledge if it's successful, which is our source of truth in this case. So this is the high-level process. So now let's see how we actually can wrap a script, let's say, to be compatible with such an architecture, with such an orchestrator. And here we have created a simple SDK where it's a pretty easy recipe how to wrap a script. The first thing is we define input and output variables, parameters, return values of the function block. This is pure Python and nothing fancy. Then the second one is to register the function, and here we will declare if the function is pure or if the function is idempotent. So this is one of our assumptions, that the engineer writing the script can actually analyze it and decide if this is the case or not. It's unfortunately not so easy to do it automatically, but when we have this, we can base on that. And then comes the fun part. We just need to adapt our script to work with the context that we get as a parameter. So we maybe need to tweak something in the script, but it shouldn't be too much in a lot of cases. And then finally, if we know how to roll back, we can also provide a rollback function. So the orchestrator will know what options do we have when we fail with an execution. So this is our building block. What can we do with it? We can include a building block in a workflow, of course, because we are talking about workflows, of course, workflows as a transaction. So this is what the workflow looks like. It's inspired by GitHub Actions and Co. So I think it's a pretty common syntax. And what we can do is we can include our functions with a referencing syntax, with versioning. We can pass the parameters in a declarative way, statically or dynamically. We can label it to access the result object. And then in the end, I hope this looks kind of familiar, this syntax. So everybody that wrote CI/CD pipeline or something like that is probably familiar with this. Okay, then we're going to have a look at the resulting architecture of this, and we will see what happens when we execute a workflow like this. So we take the workflow. This time we have a graphical representation, so it's just the 4 steps that we saw before. And as you can see, they are mapped to different workers, so we can actually deploy this functionality in, for example, a Kubernetes cluster, and scale it and place the workers in network zones however we want. This allows for quite a fancy setups, of course. But then, yeah, we send the definition. We execute it with parameters. Here, for example, we say we want to migrate the point of sale number 42. And what our engine, our workflow engine then does as a first step is just to lock the resources, eventually getting a context back. At this point, isolation is guaranteed. And once we have isolation, we can start putting jobs on a blackboard where the workers will sequentially poll and execute the tasks associated with this workflow. So this is how the final thing looks like. And we can also see that functions can coexist in different versions. That's also something important for us, that we can say, let's push a new version of the function, but not without affecting existing functionality. This is always a very scary thing. Yeah, we are approaching the end of the presentation already. Maybe some takeaways. First, the benefits of employing a locking approach. I think this is quite a different approach than what we saw until now. And pessimistic locking in particular has some very nice side effects. And the first is auditability in the network. So we can easily understand which workflow did potentially talk to a device or change the configuration on a device, for example. And we can also see which devices are currently locked. So we have like a live view which devices are currently under migration or under some other functionality that the workflow may provide. We can also manually block a device for manual intervention. So if we put a lock on a device, this will just stop or not allow any workflow to run on it. So we have a lot of manual control. And then also from the architecture idea, from the architecture that we chose, we have a lot of problems that we had in previous, or that we know from previous projects, a bit solved by design. So we have scaling, we have different versions, different network zones. We are not limited to a particular programming language, and as of now there is a Python SDK, but it's not limited to Python. Okay, and then we are already at the end. If this concept or this approach resonated with you, that's very nice for us. Feel free to scan also the QR code. We would really be happy to welcome you at the test lab and at a small Slack community. So if you are interested in learning a bit more about that, feel free to scan this QR code. And I think we have 1 or 2 minutes for questions.
We have a couple of minutes for questions. I see one in the corner there. Coming. Introduce yourself.
Thank you. Ciprian from Sunrise.
Hi.
Hi. I'm just wondering if in your use case you had a problem or not with the pessimistic locking of an aggregating device in regards to parallelism of migration flows.
Yes. In fact, during the use case, we didn't even have the locking mechanism in place. This was one of the findings after use case. What we falled back to mitigate the issue was a state machine, which included the state of a whole location. And since our source of truth known which devices were related to this location, we kind of make that locking that way around. And then it scaled very well because it was pretty much segregated. So if one location is locked, it didn't affect any other locations.
But you did not have in, let's say, one plan work, 10 sites having to be migrated, all of them affecting an aggregating device. So let's say if the first 9 sites were successful, or let's say the first 6 sites were successful, but the 7th failed, we're able to continue with site 9?
Yes, yes. The only issue we had was like a real-world limitation because the on-site teams, which would be called onto the premise early in the mornings in order to repair it and bring it back online, they are limited to several areas. So they had like some area for Zurich and some team for that. And what we did is if a location, a migration failed in one area, we did a rescheduling on the fly during the night and avoided any other migrations in this area, just to make sure that people are capable to mitigate the issues.
Thank you.
Thank you.
Any other question? We would have time for one quick question. I don't see any hands. Oh, very last second.
Claudius from Canton Schule Zug. Just a small question. What's the failure ratio? Like the safe and unsafe failure?
We don't know yet.
It's still ongoing.
This is a very new technology. We have no numbers to provide. But it is a very interesting question also to us to keep track of it. Would be a nice feedback to the authors of specific function blocks, of course.
Or did you mean the failure ratio of the migrations we did?
Or you said between fail safe and fail unsafe, right?
Success, fail safe, and fail.
Yeah.
Ah, okay.
Okay. Then it's my answer.
Okay. Well, thank you very much.
Thank you.
Yeah.